For decades, the prevailing assumption in artificial intelligence has been that size demands scale. If you want to train a model with 100 billion parameters, you need a data center. You need rows of servers humming in the dark, connected by high-speed networks, consuming megawatts of electricity. This has been the dogma of the industry. Researchers and companies alike have accepted that full precision training of ultra-large language models is impossible without massive multi-GPU clusters. It is a hard constraint imposed by the physical limits of graphics card memory. But a new system called MegaTrain is challenging that dogma. Developed by researchers from the University of Notre and Lehigh University, this technology claims to enable full precision training of 100 billion-plus parameter models on a single graphics processing unit. That is a single card, not a cluster, not a supercomputer, just one device. The implications are staggering. If true, this shifts the entire economics of artificial intelligence development. It suggests that the barrier to entry is not just capital, but architecture. To understand how this works, we have to look at the fundamental constraint. A graphics processing unit is incredibly fast at calculation, but it has limited memory. When you train a large model, you store the weights, the gradients, and the optimizer states inside that memory. This is called video random access memory. For 100 billion parameters, the data simply does not fit. The traditional solution is model parallelism. You slice the model across dozens of cards, passing data back and forth constantly. MegaTrain takes a different approach. It treats the graphics card as a transient compute engine. It does not try to store everything on the chip. Instead, it keeps the weights and optimizer states in the host memory, which is the standard random access memory of the computer itself. Here is the thing about this approach. It sounds simple in theory, but it creates a massive bottleneck. The speed at which data can move between the host memory and the graphics card is much slower than the speed at which the card can process data. If the processor has to wait for data to arrive, it sits idle. MegaTrain solves this with a pipelined double-buffered execution engine. Imagine an assembly line where one worker hands off a part to the next worker, while the first worker grabs the next raw material. By overlapping transfers and computation, the system keeps the processor busy even while data is being fetched from the slower host memory. Another key innovation involves the stateless layer templates. In standard training frameworks, the system maintains a persistent autograd graph to track how to calculate gradients. This graph consumes memory and adds overhead. MegaTrain eliminates this persistent overhead by using templates that are generated on the fly. This reduces the memory footprint significantly and allows the system to handle larger models without crashing. The results published in the research indicate that they successfully trained a 120 billion parameter model on an H200 graphics processing unit. They also reported a 1.84 times throughput improvement over DeepSpeed ZeRO-Three for smaller models. DeepSpeed is a popular library for optimizing training. This suggests that MegaTrain is not just a theoretical exercise, but offers tangible performance gains in certain scenarios. However, we must consider the trade-offs for production pipelines. The primary concern is latency. Because the system relies on host memory, the speed of training is inherently tied to the bandwidth of the connection between the processor and the memory. While it democratizes access by removing the need for a cluster, the training time might be longer than a fully optimized multi-GPU setup for the same task. If you need to train a model in a week, a single card might take 2 weeks. Is that a fair trade? There is also the question of stability. Running 100 billion parameters through a pipeline that constantly swaps data in and out of memory introduces complexity. Any interruption in the data stream could corrupt the training run. For a research lab running overnight experiments, this might be acceptable. For a production environment that needs guaranteed uptime and predictable costs, the risk profile is different. Another significant factor is the precision of the training. MegaTrain focuses on full precision training. Many modern systems use mixed precision or quantization to reduce memory usage. They store numbers in lower bits to save space. MegaTrain suggests that full precision might be necessary for certain high-fidelity tasks, and that the hardware advances are now making this feasible without quantization. This offers a new baseline for efficiency. It implies that we might not always need to sacrifice accuracy for speed. The cost-benefit analysis is where the real decision lies. A single high-end graphics card costs significantly less than a cluster of 20 cards. The electricity bill for one card is also a fraction of a cluster. For smaller organizations or individual researchers who do not have access to enterprise-grade infrastructure, this is a game changer. It levels the playing field. But for a large tech company, the opportunity cost of time might outweigh the hardware savings. If the single card takes twice as long to train, the engineers are occupied for twice as long. This shift also changes the focus of future research. Instead of optimizing internode communication and cluster scaling, the industry may pivot towards optimizing single GPU architectures and software stacks. The goal becomes squeezing more efficiency out of the individual unit rather than just adding more units together. This could lead to more powerful consumer hardware and more efficient software tools. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.